Hello there, students. Welcome back. We're going to start making some graphics about our statistical models in Octave, and we're going to be doing this using a type of diagram called a scatterplot. We certainly have seen lots of scatterplots already in this class. We just haven't been doing them yet in Octave. And then we're going to also see how we can display our statistical model that we're producing that's going to be producing our estimates of our quantity that we're doing predictions. Let me show you this little scatter diagram I've got here. Boy, there's a whole lot of points. They seem to be kind of forming a cloud of points. It seems like they're sort of clustered in a way that perhaps a linear best fit line would be a good choice here. What do I actually have here? This happens to be a scatter plot of it's just the station Howells. This is from that 10-year data set that you guys used in the last module. This happens to just be station 506, which is Howells, and it just happens to be January and for the 10-year period. And what it is on the x-axis, the independent variable is each morning's minimum temperature. And then on the y-axis, I have, as the dependent variable, I have the daily maximum temperature. So basically, we're just finding out, like, if you knew what the morning's low temperature was, can you make an estimate of what that day's maximum temperature was? And so, okay, I mean, we could have, I could have used other things. I mean, we could have talked about, predicting the amount of power being produced by a solar panel based on the cloud cover, or the amount of power being produced by a wind turbine based on the pressure gradient force near the wind turbine, or something like that. But for now, we've got just this temperature data. And I want to see what I can do with it. Well, alright, so here I've just got some screen captures to help you see what I did to make this here. I made myself a little plot where, first off, I just loaded my 10-year data, just like you did for Project 2, and I filtered it out to just keep January and just keep the station Howells. So you can see you're old pros at that kind of stuff by now. Now, the command to produce the scatter plot is remarkably simple. It's just scatter. Now, scatter makes a fairly primitive looking thing. We're going to make sure that we have it all set up the way we like it with labels and stuff like that. But it's just got two arguments for sure. In this case, I've used a version of it that has three, but we'll see that in just a second here. Now, the first argument is just a list of the x variables, what's going to be the independent variable on our plot. So like in this case, I'm using minimum temperature in the morning to predict the maximum temperature in the afternoon. That's column 6, as you'll recall from our data set. So I'm plotting all rows column 6 from my filtered version of the data set. Then the second argument to scatter is the list of all the y variable, the dependent variable, what you're trying to make predictions of. So in this case, since we're trying to use minimum temperature to predict that day's maximum temperature, we're going to choose maximum temperatures in column 5 of our data set. So we're saying all rows column 5 of our data set. I've already, in this case, I chose Howells partly because I already knew from last module that there's no missing data at that station. I might have had to filter out the missing data if otherwise. In this case, I do have an optional third parameter that I have put to scatter, and that is this, in quotation marks, filled. And that just made that the scatter diagram had little filled circles at each grid point. Each data point that we put on there. If you don't put the word filled there, I think it uses little bubbles to mark the points. There's a whole lot of different options there, but filled will be fine for what we do. You can control the color and stuff like that, but we don't really need that for our purposes here. Now, if I just ran this, it would make a scatter plot with no labels or anything like that. We want to put more stuff on there. The trouble is, there's commands to do things like put a label at the top of the diagram, or label the x-axis, or label the y-axis. The problem is, if we do that, it'll erase the current plot and put a title at the top of the new plot it's creating. We want it to hold this plot and just keep drawing something else. Okay, the command to hold this plot, don't lose it, is hold on. Okay, there's a hold on and a hold off. Okay, but hold on is what we're going to be using right now. People who are in ATS 315, the Computer Programming and Meteorology course, this is very much like the ghold command in C graphics. So you're saying, don't destroy the current plot. Let's leave that plot up, and we're going to start doing more things. And so, well, the commands to do things like put a title across the diagram is just title, and then in parentheses you provide, parentheses, and then in quotation marks you provide the string that you actually want to have, the string of characters that you actually want to have as the title. Like in this case, I just labeled it January. Feel free to put don't feel free, do put an x-axis on using the command x label. It works the same sort of way with parentheses and then in quotation marks exactly the string of characters you want to appear on the x-axis. Same thing with y label. Pretty straightforward once you know that hold on trick. Alright, so you get a nice looking plot that looks something like this, and oh, it's not exactly the most elegant plot you could have ever made, but it certainly gets the job done or whatever. And what we'd really like to do next is actually put the statistical model that we're creating, this best fit line that is going to be producing our estimates there, onto the graph as well. Alright, well first we need to actually develop the model. We got to do the calculations of terms like B0 and B1 and so on. So since we're just using a simple linear model, our model is just yi hat is equal to this very basic y-intercept plus slope type term, B0 plus B1 times x of I. So for any value of xi, we now can come up with an estimate that's going to be just on that line, y hat of I. Okay, pretty straightforward there. Alright, so if we do this, how are we going to actually make this work in Octave? Well, remember we have that polyfit command. Polyfit is what creates a little matrix that holds the regression parameters beta naught and beta 1, or b naught and b1 and so on. So like we use the polyfit command here where we're saying excuse me, the x's are going to be the data in all rows column 6. That's our x's on our independent variable in our calculation. And data gen all rows column 5 is our dependent variable, our y's. Okay, and notice we have a comma 1 there to tell it it's going to make a first order model to make predictions here. Now remember I came up with this little trick here of saying put that in like a temporary variable, like I called it btemp, and then use that flip left right command to actually rearrange them into a way that makes more sense. You don't have to do that, but I would recommend it because it just makes a little bit more intuitive sense. That way, at least they're in order. B1, B parenthesis 1 is that beta naught variable. I actually called it just literally B0 on there. This was probably not the best choice. Probably something like beta 0 would have been a better choice. And then B2, B in parentheses 2, the second element of the array becomes this new constant B1. Again, beta 1 might have been a better choice of a name there or something like that, just so that I could keep it straight. Okay, but I just wanted to like kind of pull them out and so we can see that, okay, this is the y-intercept. It's going to be called B0, and it is the first element of that B array, and so on. All right, we can work with this. If this is confusing to you, send me email. We'll gladly get this sorted out when you're doing this in the project. All right, so now when we have these parameters, we now have values of B0 and B1 that would be perfectly fine for our regression line. It is the best fit line and so on. All right, what we need to do is come up with some way then to plot that. We're going to come up with a range of values of x and compute the value of y at each of those values of x. Well, here, if I actually look at my data from Howells in January, I see that x seems to range from roughly -30 to about 5 degrees Celsius. Okay, so if that's my typical range here for January temperatures or whatever, what I'm going to do is I'm going to create my statistical model by saying x is just going to be the range from -30 to 5 in steps of 1. So what this does here, we did a lot of this stuff in Project 1, where we made an array now of x is equal to, and then -30, -29, negative, all the way up to 5. All right, so we've got, I don't know, what would that be, 36 values of x. Then we're going to just compute the value of y as a function of x. Here, y is equal to b0 plus b1 times x. I mean, this is pretty fancy schmancy math going on here because, I mean, x is an array, now y is an array, but I mean, it worked. Okay, this is just simple linear algebra type stuff. Cool. All right. Now, we can actually then plot that on the same scatter diagram that we are currently holding by saying plot. Plot x, comma, y, comma. Now, if you want to, you can have, like, I made the line thicker with line width, comma, 5, which makes the line 5 points wide. You wouldn't have to. You could just say x, comma, y. That would be fine. There are a whole bunch of other arguments you can add here that change the way the line's color is, or if it's dashed or whatever. But this is fine. Again, we're not trying to discover all the secrets of Octave. We just want something that teaches us something instructive about statistical models. So this would be fine. Plot, by the way, is a really handy little tool here. As anytime you have some variable, some data in one array and some data in another, plot the first one comma the second one will make you a lovely little line diagram. It's the easiest thing in in Octave. You might use that actually for part of your project. So if you actually produce your plot, it'll look something like this. Now I have to admit, on the plot that you're seeing right there, I cheated. That I actually drew that regression, that best fit line on there in PowerPoint. Okay, you'll see why in just a little second here. But your plot will look a lot like that. We can do, that was a linear model, a first order model. The highest power in our statistical model was x of I. It wasn't raised, it wasn't squared or cubed or to the 27th power or anything like that. But we could do higher order models too. For example, let's say we wanted to have a third order model where we had a xi term, an xi squared term, an xi cubed term as well. So our model is that our forecasts of y at time I, or the ith observation of y I hat, is equal to b naught plus b1 times x of I plus b2 times x of I squared plus b3 times x of I cubed. I'm not sure I'd recommend making a third order model unless you had some reason to think that the cubed term is important, but overall it's going to be okay. Now, how are we going to do this in our Octave? To make a third order polynomial fit to our data, a best fit curve, if you will, well, it's basically exactly the same thing. We're going to still use that polyfit command. We're still going to send it that we want all rows column 6 of our data to be the x data, all rows column 5 of our array to be the dependent variable, the y's, but we're going to tell it comma 3 to say make this a third order polynomial. Now again, stuff that into a temporary array, something like a btemp or something, or beta temp, and then use the flip LR to flip it left to right. It'll just be easier. You're reversing the orders of these indices and it'll just be better. Because then, okay, you're just offset by 1. You're like B0 term is just the first element of the B array. B1 is just the second element of the B array, and so on, okay? Again, that just makes it more clear to me, but, you know, if you want to do it differently, again, feel free to ask. We can get this sorted out as to the best way to do it. Then it's time to make the actual statistical model. Once again, we're going to compute the value of x. We're going to create a little array of x's that go over the whole range that we want to make these forecasts, like from -30 to 5 degrees Celsius, just like we did before. And our y is just that model. Now it's just b naught plus b1 times x plus b2 times x squared plus b3 times x cubed. What the heck is that dot caret? In general, caret is how you like raise something to the power. A caret 2 is a squared, or c caret 3 is c cubed. The only difference is when you're talking about an array. An x is an array. It has rows and columns. It has one column but lots of rows. To actually like cube each element of that array, it's not caret, it's dot caret. Okay, this works very much the way like the dot multiply or the dot divide operator did, gosh, way back in Project 1. So just pay attention to that. You'll get a very illustrative error message if you do this wrong. And then again, we're just going to plot that same set of curves, x and y, and you get something that looks like this. Now, it might be a little hard to tell on the screen there, but that model that we created is a curve. It's not quite straight. Honestly, the x squared, that b2 term, and the b3 term that it showed up on the xi cubed term are both kind of small. I mean, the reality is this equation is fairly linear. The relationship between these data sets is pretty linear. So, I mean, we didn't end up with some like, you know, inflection curve or anything like that associated with this. We just kind of got a slightly bent curve. Okay, so in other words, I don't know that I would have gone to a third order model when realistically I'm not sure this looks all that different than the linear model, but whatever. Now, hypothetically, you should be able to go in, when you bring up these plots in Octave, go up into the window where the plots are and hit File and then hit Save As, put them a name like scatter.jpg, and you should be able to save them. I don't know why, but for some reason that's not working for me. It works for plots that don't have these labels on there or don't have that regression line. No, I'm sorry. It's when I overlay that regression line on there. They don't work after that. despite the fact that I worked my way through examples in online that I found, and it worked just fine. So I don't know what I'm doing wrong. So I have some email messages out to some of my colleagues who might know, oh, don't be silly, you missed the semicolon here or something like that. I'm sure it's a small thing. What I'll do is, when I get it figured out as to why I wasn't able to make JPEGs of these so that you could actually save your plots, I'll include the instructions in the Project 3 details. It's going to be something very simple, like hold on has to have a semicolon after it or something. Something that was just not mentioned in the exercise that I worked through. Hey, I want to show you one more thing that kind of relates to the tricky question. I think it was number 14 or something back in the last module. There was a question where you did something similar to this. You were actually comparing two different stations. Now we're just comparing one station's minimum to its maximum, but it's the same kind of problem. You computed a correlation based on 1 month, well, 1 month of the year, but through 10 years of data. So like here's 31 times 10 is 310 data points for Howells, Nebraska. And we computed, in this case I'm going to compute the correlation between the low temperature and the high temperature. And I get a pretty darn good correlation, 0.7789. That is a pretty high correlation. And of course, you look at that scatter diagram and it's pretty obvious that there's a correlation here. I mean, that clearly there's some pattern to the highs and knowing the low temperature does tell you something about the high temperature. Now, in the tricky question on the last project, I said, well, now go do that not just for January, but for all of the months of the year. 12 months of the year times 10 years times, 10 years times 365 days, and you got like 3,000 data points. So you're going to have a plot that looks something like this, where I have all 3,600 and some odd observations from Howells. I have the minimum temperature on the x-axis and the maximum temperature on the y-axis, and I get this big cloud of data where I can see, oh my goodness, it's clearly going to have a good linear fit there. And in fact, if I compute the correlation between the two of these things, I get a much higher number. I got correlation is equal to 0.927. My goodness, that is a very high correlation. There's a very high correlation between the minimum temperature and the maximum temperature over the course of the year, like each day of the year, much higher than just when looking at January. And the question is why? Why is the correlation better when we look at the whole year versus when we just look at like the data from 1 month for 10 different years? This is a difficult question to articulate. Here's the deal. Remember, correlation is fundamentally about percent variance explained. It's actually the square root of percent variance explained. So if we are saying that the correlation is higher, what we're saying is this relationship is explaining more of the variability. Well, take a look at these two data. We're trying to explain the variability in the maximum temperatures. Inside of just the month of January, the variability of the temperatures is kind of a day-to-day thing. Like, today it was a little bit of a warm January day, and the low temperature was fairly high, and the high temperature was fairly high. Tomorrow, a cold front goes through, and tomorrow the low temperature is quite low, but the high temperature isn't very high. But it's just sort of a day-to-day weather variability thing. Over the course of a year, though, the main thing that's going on is the summer cycle. I mean, if I know the low temperature last night was 72 degrees, I can make a pretty good guess as to what the high temperature is. It isn't going to be 74. It's going to, I mean, we're talking a hot summer day. It's going to be a high temperature there. On the other hand, if the low temperature last night was negative 20 Fahrenheit, the high temperature is not going to be 72, okay? There's a pretty strong relationship over the course of the year. Yes, there's still day-to-day variability, but we have actually explained a lot of the variability by understanding the seasonal cycle to these low temperatures and how that's related to the maximum temperatures. That may not be the most articulate explanation I've ever given, but I kind of wanted to at least point you to what kind of thing I was looking for on that question back on Project 2. There's more variability in the Y data when we go to the year, but more of it is again explained by the annual cycle, and so as a consequence, more of the variance is explained, we end up with a higher percent variance explained, we get a higher correlation. All right, that is all we needed in this lecture. I think you're going to have fun with these scatter plots. Please let me know if you have any questions. We're almost ready to start Project 3.